Hello everyone, my name is Taegyu Kim from Purdue University. Today I will talk about MAYDAY, a forensic tool to investigate drone accidents by connecting the control model to control program. The drone or robotic aerial vehicle is a type of a cyber-physical system that interacts with the physical world. They are used in a wide range of applications such as surveillance and transportation. However, drones have many control-related security and safety issues, and we have seen increasing reports about drone accidents. Now, let me introduce drone control model and control program. The drone control system consists of mission, sensor, controller, and motor modules. It controls the physical operations during the flight for all 6 degrees of freedom, X, Y, Z axis, and roll, pitch, yaw. The sensing, control actuation, and the physical aerodynamics create a control loop. All these are captured by control model. The control model is implemented in the control program. However, like any program, a control program has bugs. In this paper, we focus on a specific type of bugs called Control-Semantic bugs. A Control-Semantic bug is an incorrect or incomplete implementation of the control model. It can be the root cause of a drone accident. Next, I will tell you a sample accident story. In this accident, a drone starts its mission from waypoint 1, moving west waypoint 3, and then moving north waypoint 4. At first, the drone flies west normally. During the flight, it accepts an operational command to change x-axis velocity control gain parameter. After the change, the drone continues to fly normally. However, when the drone gets closer to the turning point 3, it suddenly loses stability. The instability continues all the way throughout the rest of the flight. In order to investigate this accident, MAYDAY should be able to identify the root cause in the control program. I will show you how to investigate it later in the evaluation part. Unfortunately, such a root cause hidden in the control program is very hard to investigate. There are 2 gaps to overcome. First, there is a domain gap between the control and the program domains. There are control level logs for forensic analysis supported by major drone control software, but there are no program level logs. Even if program level logs are recorded, it is hard to trace the corrupted control state back to the program level bug. Second, there is a time gap between the attack time and its impacted time. The bad command was injected earlier in the flight, but the unstable control state starts to appear later in the flight. Therefore, we develop our solution, MAYDAY, to bridge the gaps to enable cross-domain investigation from the accident impact all the way to the program level bug. MAYDAY covers 3 phases in this workflow. The first phase is offline control program analysis and instrumentation to instrument, analyze the control program, and add logging functionality to the program. In the second phase, the instrumented program is deployed in the drone for real operations. In the third and unfortunate phase of a drone accident, MAYDAY will perform investigation by analyzing the drone's black box with both control and program logs. I will explain these steps in details in the next few slides. Let me first explain how to model the drone controller organization as a control variable dependency graph or CVDG. Let's take the x-axis control as an example. The x-axis is controlled by a cascade of primitive controllers. The primitive controllers control the drone's position, velocity, and acceleration respectively. We map them in a cascade in the CVDG. Furthermore, the 6 degrees of freedom controllers X, Y, Z, roll, pitch, yaw have an interdependency. We also map them to the CVDG. Next, we establish the mapping between the control model and control program. The mapping has 2 aspects. First, we map the control model variable to the corresponding control program variables. The variables include the control parameter variables in the red circle and the control reference variables in the purple color, and the control state variable in the yellow color. The second aspect of the mapping is to map the control model data flows to the control program execution paths that implement the data flows. As an example, in the control model, the z-axis acceleration reference is determined by z-axis velocity state, reference, and parameter. Such a data flow corresponds to the code snippet that I just swept through. Based on the model-program mapping, we can now enhance the control program with logging. Control and vehicle level logs are already recorded by default in major drone programs such as ArduPilot and PX4. The logging is performed by a number of control level logging functions. To find the program level bug that causes an accident, we also need to record control program execution. Such a program execution is enabled by MAYDAY. This is enabled by LLVM level analysis and instrumentation, guided by the mapping between the control model and control program. Now, the drone will record both control level and program level logs during its missions. If an accident happened, the black box of the drone will contain both types of logs, which will be used by MAYDAY to perform cross-domain investigation. Now, let me explain the investigation starting from the control level investigation. Control level investigation is based on the control level logs, especially the values of control state, reference, and parameter variables over time. For example, the figure on the right side shows the values of a drone's velocity state and reference. You can see this is bad because the state can no longer track the reference. Among all the malfunctioning controllers, MAYDAY will use the control logs to identify the first one that went wrong or digressing. We call it the initial digression controller. We also determine the corrupted control variable shown as the red color nodes in the figure on the left. In this specific example, the initial digression controller is the x-axis velocity controller. The corrupted control variable is x-axis state variable because it cannot track the velocity reference. The control log also tells us the initial digression time represented by the control loop iteration. Then MAYDAY will infer the control level corruption path, which is the control model data flow that leads to the corruption of the control variable identified earlier. The inference is based on CVDG, which models the causality between the control model variables. Once the control level corruption is determined, we are ready to move the investigation from the control domain to the program domain. The transition point crossing the domains is the corrupted control variable at the sink of the control level corruption path. Remember, we have a mapping between control level and program level variables. Using this mapping, we can identify the program level variable that corresponds to the corrupted control variable. Now, we are ready to perform program level investigation starting from the corrupted program variable. Recall that MAYDAY has inferred the control level corruption path from the attack input to the initial digression. The goal of the program level investigation is to find the corresponding program level corruption path by backtracking the program level log. The path is shown in the animation. Once the program level corruption path is found, we can identify all the control program basic blocks that were executed along the path, and the bug that caused the corruption can be found by examining the program source code that corresponds to those basic blocks. As you will see next, MAYDAY keeps the number of the basic blocks small for the final bug identification. For effectiveness, MAYDAY investigated 10 realistic cases. These cases are constructed by the real bugs found in the very popular ArduPilot control program. Then, MAYDAY succeeded in localizing bugs with a small number of basic blocks from 7 to 50. Now, MAYDAY is ready to investigate the case that I demoed earlier. Investigators first analyze the control level log to find an initial digression point. MAYDAY identifies XY axis velocity controller as an initial digression controller with the XY axis acceleration reference as corrupted control variables. Then, MAYDAY identifies the corresponding control level corruption path and control program variables. by combining control level corruption passes and the program level logs, including control program data flows in the blue color, MAYDAY traces the initial digression point back to the attack input in the program domain. Then MAYDAY pinpoints the attack input is control gain KP parameter. Remember, attackers change this parameter during the initial segment of the flight. Then MAYDAY identifies the basic blocks on the program level corruption path. On the program level corruption path affected by KP parameter, it turns out range check on KP parameter is totally missing. This means that an attacker can set KP parameter to any value and the program just accepts it. This is dangerous. We note that this was a real bug in the ArduPilot that was corrected. We also performed overhead evaluation on MAYDAY with a real drone running ArduPilot. We measured the execution times of a wide range of software real-time tasks in ArduPilot with and without MAYDAY. Our result shows that the execution time with MAYDAY is longer than without MAYDAY. However, tasks execution times with MAYDAY still are shorter than the soft real-time deadlines. In conclusion, drone accident may be caused by Control-Semantic bugs. However, control level logs alone are not sufficient for bug tracing. To overcome this limitation, we propose MAYDAY, a cross-domain accident investigation tool. This can be achieved by bridging the domain and time gaps, mapping control model to the control program, integrating control level and program level logging, and connecting control level and program level investigation. This is my end of talk. Thank you very much for your attention.